All right, so here's another example of a linear programming problem. Fairly similar to the last one, slightly different, but same idea. So let's say you need to buy some filing cabinets. You know that steel cabinets cost $10 per unit. They require 6 square feet of floor space and hold 8 cubic feet of files. Titanium cabinets cost $20 per unit, require 8 square feet of floor space, and hold 12 cubic feet of files. You've been given $140 for this purchase, though you don't have to spend all of it. The office has room for no more than 72 square feet of cabinets. How many of which model should you buy in order to maximize storage volume? Okay. So what we're going to do is I've literally, if you saw my first example, this is the same format as the first example. I've got the same steps for us, and we'll just kind of follow through with them. Okay, so first thing I'm going to do is figure out what are X and Y going to represent. So in this case, the question is, right, the question is asking how many of which model should you buy? So what are the models? We have titanium, and then we have, wasn't the other one steel? Yeah, steel. Okay, so we have steel and titanium. So let's let X equal the number of steel cabinets. Okay, so we'll zoom in here. X is going to be the number of steel cabinets and Y is going to be the number of titanium cabinets. Okay, so that's our first step. The next step is to write an objective function, and our objective function is where we're going to decide how much money we're going to make based off of these variables here. So if X really stands for the number of steel cabinets and Y stands for the number of titanium cabinets, how much money are we going to make? Well, how much do we... or no, it's actually not how much money we're going to make. I apologize. The question was, how many should we buy in order to maximize storage volume? So this is not a question of maximizing money. It's a question of maximizing storage volume. And we're willing to spend a certain amount of money, up to $140. So if we're trying to maximize storage volume, we need to look at what it says about volume. Steel cabinets cost $10 per unit, require 6 square feet of floor space, and hold 8 cubic feet of files. So if our steel cabinets are holding 8 cubic feet of files, and X is the number that we sell, then I'm going to say that the amount of volume we get for that is going to be 8 times X. That's the amount of volume we're going to get out of our steel cabinets. How much volume are we going to get out of our titanium cabinets? Well, they cost $20, require 8 square feet of floor space, and they hold 12 cubic feet of files. So they're gonna give us 12 cubic feet per cabinet. Okay? So our objective function then is however many steel cabinets we get, we're going to multiply by 8, and however many titanium cabinets we get, we're going to multiply by 12. This will give us the total amount of storage volume that we're able to get out of our cabinets. So we're going to try to maximize this later in step 5. Okay, step 3, they want us to write a system of inequalities that represent the constraints, and the constraints are just the things that are limiting us here. If we could, we would just buy a bunch of titanium cabinets, because the titanium cabinets give us 12 cubic feet per cabinet, which is way better than the steel. But the problem is that the titanium costs twice as much, and so, we've got some constraints here. All right, so what are our constraints? Let's look at it. Steel cabinets, okay, so they have a cost. There's a cost constraint. We only have $140. Okay, so let's write that down. So the first constraint we want to worry about is cost. What's another constraint that we want to worry about here? They require floor space, right? So the steel cabinets require 6 square feet of floor space. The titanium cabinets require 8 square feet of floor space. And what was the constraint on floor space? So the office has room for no more than 72 square feet. So let's say that floor space is another issue. That's another constraint we're going to have to work with. Are there any other constraints that we need to work with? So we got money, floor space, the volume, hold 8 cubic feet of files. That's actually our objective function. That's what we're trying to maximize. So we're not limited on the amount of cubic feet or the volume. So I think we're good, actually. So the question now becomes, what is the constraint as far as the cost goes? So, all right, let's write this out. We only have $140, so however much we spend needs to be less than or equal to 140. Okay? And what we're going to write over here on the left side of this inequality is how much we spend. So if the steel cabinets are costing $10 per unit, how much are we going to spend on the steel units? X was the number of steel units that we have. So what we're going to do is we're going to say 10 times X is the amount of money that we're going to spend on the steel units. Okay? X was the number of steel units. 10 is how much they cost per unit, so 10 times X is the amount of money that we'll be spending on the steel. How much money are we going to be spending on the titanium? Well, if they cost 20 per cabinet and we have Y of them, then the amount of money that we're going to be spending on the titanium cabinets is 20Y. So the amount of money we spend in total is going to be 10 times the number of steel cabinets plus 20 times the number of titanium cabinets. Altogether, that needs to be less than or equal to 140. Okay, that's our cost constraint. What about our floor space constraint? So our floor space constraint, we're saying that we need, for steel cabinets, we need 6 square feet of floor space. So what we should do is let's go ahead and say 6 times the number of steel cabinets we get. That's going to be the amount of floor space we need for the steel cabinets. What about the titanium cabinets? They require, where does it say? Titanium cabinets require 8 square feet of floor space. So we're going to need 8 square feet of floor space for those. And how many of those do we have? We have Y of those. How much floor space are we working with here? It said it has no more room for no more than 72 square feet of floor space. So we're going to say that altogether, the total floor space that we use for the steel and the titanium cabinets needs to be less than or equal to 72. Those are our two equations for our constraints. You may, by the way, you may have many constraints. You might not have a whole lot. Like sometimes we do problems like this and there are only 2 constraints. Sometimes there are like 6 constraints. So it just depends on the problem. Okay? All right, so that's step 3. So we've got our system of inequalities. Step 4 is we're supposed to graph the feasible region and identify the vertices. So what we're going to do is we're going to take these inequalities and we're going to graph them, and then we're going to find the corners of the feasible region. So let's go ahead and actually, I'm going to zoom in just a little bit. And before we graph these, what I want to do is I want to actually get Y all by itself. So I'm going to move over just a little bit so I can see. And on this first one here, I'm going to get Y all by itself. So we've got 10x plus 20y is less than or equal to 140. I'm going to subtract 10x from both sides. And when I do that, I'm going to get 20y is less than or equal to negative 10x plus 140. And now I'm going to divide by 20. Everybody's going to get divided by 20. And so this equation now is going to be y is less than or equal to, all right, so negative 10 over 20x is going to give us negative 1/2 x plus, and then 140 over 20 is 7. So this right here in yellow is our first inequality that we're going to graph. And before I graph it, I'm going to solve the other inequality. Okay, so that's our first one. The next inequality, let's So I'm going to give us a little space here. The next inequality, we're going to subtract 6x from both sides. So we're going to have 8y is less than or equal to negative 6x plus 72. And then we're going to divide by 8. Everybody gets divided by 8. So we're going to have y is less than or equal to negative 6 over 8. I'm going to reduce that to negative 3 over 4. You can leave it as negative 6 over 8. It's not wrong. I'm just going to reduce it a little bit. And then 72 over 8 is 9. So this is our second inequality. And what we're going to do is we're going to graph both of these, and then we're going to shade. It looks like we're going to shade below on these. Okay, so we're going to shade underneath them. So, all right, let's come over. And that's not what I wanted to do. All right, so we'll come over and we'll graph these. So the first one I'll do with a dark blue. All right, so the first one is y is less than or equal to negative 1/2 x plus 7. So let's go up to 7. And we're going to go negative 1 over 2. So we're going to get down 1, right 2, down 1, right 2, down 1, right 2. And we'll go ahead and draw the line there. So we'll go ahead and graph that. Okay, so that's our blue one. And now we'll come over to the second inequality. And we need to start at 9, and then we're going to go down 3 over 4. So we'll start up at 9, and we'll go down 3 over 4, down 3 over 4, down 3 over 4. All right, and we'll go ahead and draw the straight line there. Okay, so here's our straight line for that one. And now what we're going to do is we're going to go ahead and shade these. So let's shade the first one. So this was our blue one, so negative 1/2 x plus 7. We're going to go ahead and shade below on that. Let me get my pencil out here. Okay, so we're going to shade below the blue one. So everything below that blue line there, we are going to shade. Okay, so that's the blue one. And now we're going to shade everything below the orange line. And I'm going to shade sideways here on this one. So we're going to shade everything below the orange. This isn't nearly as satisfying on an iPad as it is on like an actual sheet of paper. Okay. So what I'm going to do now is I'm going to actually go in and shade the overlap area, so the area where they both overlap. And so what that is going to be is it's going to be along this left side here. I'm going to go along the bottom. And then this area, so we're going to go along this orange line here. And then we're going to go along the blue line here because we've got to be shaded below on both of them. Siri thinks I was just talking to her. That's weird. All right, and then what I'm going to do is I'm going to shade in this entire area here. Okay, so only below the blue line here, and then only below the orange line here. We got to shade only the areas where they were both filled in. Okay, so right here, this dark black area here is our feasible region. So these are all the potential combinations we could do of steel and titanium cabinets without spending more than $140 and without going over 72 square feet. So what we're going to do now is we're going to identify the vertices. Okay, so I'm going to come in and do this again with a kind of yellow so that you can see them. So here's one of them. Here's a vertex. And again, we're just looking for the corners. Okay, we're not looking for straight edges. We're looking for corners where things come together. Here's another one. And then I'm going to say that the last one is right there. So those are our 4 corners, or our vertices, is what we call them. And what we're going to do now is we're going to take those vertices and we're going to plug them into our objective function, which was up here, and we're going to see which one of these yields the most amount of storage volume in cubic feet. Okay, so let's recopy the objective function. So we'll say that f of x comma y was 8x plus 12y. And what we're going to do is I'm just going to scroll down here and zoom in just a little bit. And we're going to write down each coordinate pair. Okay, so our first coordinate pair that I'm going to start out at is 0, 0. And again, let's do those in red and green for you. So 0 for the x, and then 0 for the y. That's our first coordinate pair. We'll see how much storage volume that generates. The second coordinate pair, so I'm going to go this way. So we're starting here. The next coordinate pair I'm going up to is at 0, 7. So 0 for the x, and then 7 for the y value. That's obviously going to be better than 0, 0. The next one I want to look at is right here at, looks to me like 8 for the x, and then 3 for the y. So 8 for the x, and then 3 for the y. And then the last one I want to check is right here, and it happens to be at 12 for the x and 0 for the y. It would be interesting if that one was actually the one who produced the most. 0 for y. Okay, so all we're going to do now is we're going to take this objective function right here, and we're going to multiply the x value by 8 and the y value by 12 and see which one of these turns the biggest amount of storage space. So we're going to do 8 times the x. I'm just going to write these all out here. That way I don't have to change between colors so much. And then we're going to add 12 times the y for each one of these. Okay, so the x coordinate on the first one here was 0, and the y coordinate was 0. On the second one, the x coordinate was 0, the y coordinate was 7. On the third one here, the x coordinate was 8, the y coordinate was 3. And on the third one here, the x coordinate was 12, and the y coordinate was 0. So now all we're going to do is come through and figure out, okay, who generates the most storage volume. Okay, 8 times 0 plus 12 times 0 is 0 plus 0. 8 times 0 is 0. 12 times 7 is 84. 8 times 8 is 64. 12 times 3 is 36. 8 times 12 is 96. And 12 times 0 is 0. So let's just see which one of these generated the most storage volume. So that's 0. That's obviously not it. This is 84. 64 plus 36 is 100. And 96 plus 0 is 96. So this was actually a pretty close race here. And it looks like 100 is going to be the most optimal storage volume. So our answer here will be to purchase 8 steel cabinets and 3 titanium can't spell today cabinets for a volume of 100 cubic feet of storage. All right, so that's our optimal answer there. And let's just go back and recap each step of the process here. All right, so we're zoomed out. Okay, so we've got our problem here. The first step was to decide what X and Y we're going to represent. So we let X, and so the way I figure that out is I look at the question, how many of which model should you buy? So we've got two different kinds of models. We have steel cabinets and we have titanium cabinets. So X was the number of steel cabinets, Y was the number of titanium cabinets. And then our objective function that we wrote was the amount of money we were, or not the amount of money, the amount of storage we were going to get, the amount of volume we were going to get was going to be 8 times the number of steel cabinets, because each steel cabinet gave us 8 cubic feet. And then each titanium cabinet gave us 12 cubic feet. So we added 12 times Y. And then from there, we went on and wrote our constraints. So our constraints in this case were we had a cost constraint and we had a floor space constraint. The cost constraint was that we needed to spend less than or equal to $40. The floor space constraint was that we needed to have less than or equal to 72 feet of floor space. Okay, so what we did was we took these inequalities and we solved them down into slope-intercept form. So we got the y by itself so that we could graph them. So we graphed each one, and then we shaded below for both of them. And then that gave us the feasible region here. So we shaded in the spot where everything had been shaded. So there was some orange shading and some blue shading. The black shading is where the orange and blue were both shaded in. Notice how we didn't shade in black up here because only the orange was shaded in up here. There was no blue up here. Also, there was no orange here, so we didn't shade this in dark black. Okay, next thing we did was we identified the vertices. So we found all the corners. So 0, 0 is a corner, 0, 7 is a corner, 8, 3 is a corner, and then 12, 0 was a corner. And then what we did was we plugged in, we tried each vertex, and we found that 8, 3 happened to create the most storage space at 100 cubic feet. And so that's our answer.